Now what happens if we have a region that is bounded away from the x-axis that gets rotated about the x-axis? For example, a region that lies strictly above the x-axis that's generated by, say, two functions, the region between two functions between 2 points, like this. Well, when we take this sort of thing, we rotate it around the x-axis, we get a solid of revolution, but it has a big hole in it. And all of the, all the cross sections have holes in them. They look like washers, like that. So this is often called the washer method. It's not really a lot different from the disk method. It's just that, well, our cross sections are now circles with circular holes in them. So how do we go about finding the volume here? Well, one way is to say, okay, let's figure out what the area of a washer is. I have a preferred way of doing this, which is not saying, hey, what's the area of a washer? I prefer to think of this as our volume via the washer method is really some bigger volume minus the volume of the hole on the inside. Here's our shape. It's something with a hole cut out of it. Let's take the volume of the whole shape and then just subtract the volume of the hole. Great. So since the big shape was determined by the function f, its volume is the integral from a to b of pi f x squared dx. Since the hole was bounded by the function g, then its volume is the integral from a to b pi g of x squared dx. So subtract one from the other. Since I'm integrating from a to b in both cases, and since I've got this factor of pi, I can put them under the same integral sign, factor out a pi, and I have the integral from a to b of pi times f of x squared minus g of x squared dx. Fantastic. So let's do an example. Let's find the volume of the solid generated by rotating the region bounded by y equal to 1 over x, y equal to 1 over the square root of x equal to 1, and x equal to 4 about the x-axis. I guess saying x equal to 1 was kind of redundant because if you draw 1 over x and 1 over root x, they meet where x is equal to 1. And once you have x equal to 4, then it describes a region, but whatever. Anyways, we care about which one is the top function and which one is the bottom function. This is very similar to the area between two curves. The function on the top, the function with bigger y values, is going to be our f, and we're going to subtract the smaller function, the function at the bottom. This is going to be our g. So the volume here is going to be, and I'm not going to draw out the picture, but you can if you want to. The volume is going to be the integral from 1 to 4, and that's given to us, of pi times the bigger function, which is 1 over root x squared, minus the smaller function, which is 1 over x squared dx. And simplifying, we have the integral from 1 to 4 of pi of 1 over root x squared is 1 over x, minus 1 over x squared is that. And let's even rewrite that second guy as x to the minus 2. Why? Because we should recognize 1 over x as the derivative of the natural log of x, so the antiderivative of that guy will be the natural log of the absolute value of x. Great. Over here, x to the minus 2, its antiderivative is x to the minus 1, divided by the new power is the same as divided by negative 1, so I get plus 1. Great. It's going from 1 to 4. Now let's plug in. This is pi times the natural logarithm of 4 plus 4 to the minus 1, that's 1/4, minus pi times the natural logarithm of 1 plus 1 to the minus 1, which is 1. Now the natural logarithm of 1 is 0. And what do we get at the end of the day? We get pi times the natural logarithm of 4 plus pi over 4 minus pi, which is pi times the natural logarithm of 4 minus 3 pi over 4. Now it's probably worth it to make sure that this is actually giving us a positive answer, because this is supposed to be a volume. Well, this will give us a positive number so long as the natural logarithm of 4 is bigger than 3/4, because then pi times that will be bigger than 3/4 of pi. Well, 4 is bigger than e, so since the natural logarithm of e is 1, the natural logarithm of 4 is bigger than 1. So this is going to be bigger than pi times 1. It's bigger than pi, so this whole thing is bigger than pi minus 3 pi over 4, so it's positive. Alright, so here's question 3. I'd like you to find the volume of the solid obtained by rotating this region right here about the x-axis. So that is the region that is bounded by y equal to x squared and y equal to 2x, and between 0 and 2. Go ahead. Okay, so what happens if we decide to rotate about another axis? And the only other possibility we're going to consider here is the y-axis. And we're going to have another method that works out here called the cylindrical shells, but sometimes we can try to do the disk or washer method anyways. What we have to do, though, is we have to integrate over y instead of x. So we need to represent the curves as x is a function of y. And then what we're going to get is the volume is going to be the integral from c to d, where c and d are limits over y, of pi times f of y squared minus g of y squared dy, where f of y is the function that is on the right and g of y is the function that's on the left. Or if the region touches the y-axis, like the first set of things we did with the disk method, then we could just get rid of the g of y and just have f of y squared. But let's look at this over here. So we're rotating this about the y-axis, and the curve on the right is x equal to 1. So here our f of y is going to be equal to 1. Our curve on the left is y is equal to the square root of x. So if y is equal to the square root of x, I can square both sides, and I have x is equal to y squared. So my g of y is going to be y squared. That's the thing on the left. And notice that we're going from y equal to 0 up to the y coordinate of this point up here, and that's just 1 comma 1. So we're going from c equal to 0 to d equal to 1. So our volume is the integral from 0 to 1 of pi times f of y squared. Again, f of y is this guy right here, so that's 1 squared minus g of y squared. That's the left curve. So, because to the left is the smaller direction in the x direction, so a smaller function will be to the left. So that's minus g of y squared. G of y is y squared, so we get y squared squared dy. This gives us the integral from 0 to 1, pi times 1 minus y to the 4th dy, which gives us pi times y minus y to the 5th over 5 from 0 to 1. When you plug in 0, you get nothing. When you plug in 1, you get 1 minus 1/5. So we get 4 pi over 5. That's going to be the volume there. Okay, question 4. Let's find the volume of the solid that's generated by rotating this region, which is bounded by y equal to 2x minus x squared, and the x-axis about the y-axis. And I'd like to note that this region lies between y equal to 0 and y equal to 1, and also that if you solve for x, you get x is equal to 1 plus or minus the square root of 1 minus y when you solve here. So this will give you your two functions of y. Figure out which one is bigger than the other. Go ahead.